guys, so here we're going to do my favorite type of calculations. They're by far the easiest, and they're trying to figure out what happens to certain concentrations during an equilibrium reaction or reversible reaction. So you need your notes, and you'll definitely need your calculator for this as well. We're going to go through how to write an equilibrium expression, figure out what the capital K is, what that stands for, how to solve for K, and what happens with the magnitude of K. So here we have a basic reaction. We've put letters in there instead of elements just to simplify it. But the lowercase letters are representing the coefficients. The uppercase letters are representing different elements that could be in here. So if you ever are asked for an equilibrium expression, all this is that you have a value k, and we'll go through what k is in just a bit, and that is equal to the products to whatever power their coefficient is. So the coefficient essentially becomes an exponent over the reactants. And I'm just going to use N and M just to kind of help me out. But here, let's take a look. So I'm going to use my products first. So K is equal to my product. So I have one product, C, and we're talking about concentration, so I'm going to put it in these brackets. These brackets mean molarity, and they're another way of kind of showing molarity. That big C is raised to the C power, and that's just, again, the coefficient. It could be a number, 3, 4, whatever, times capital D to the D power, and again, this is just kind of showing you to simplify it, over the concentration of A to whatever its coefficient is, times the concentration of B times whatever its coefficient is. So if you ever ask for an equilibrium expression, this is just a general reaction to do it. Let's give you an actual example here. So here we have 2N2O5 gaseous is in equilibrium with 4NO2 gas and oxygen gas. So if we want an equilibrium expression, we set this all equal to K, and we're going to take the products first. So let's do the first product here, which is NO2, and I'm writing the brackets around it to show the concentration, and that's raised to the fourth power because that coefficient 4 ends up becoming an exponent. Here we're going to multiply it by the next product, which is oxygen. And oxygen doesn't have a coefficient, it's an imaginary 1, but anything raised to the 1 power is just itself. And we put it over whatever the reactants are. So the reactant is the concentration of N2O5, and that's just raised to the second power. So if you're asked for an equilibrium expression, this is all we need. It's really simple, nice and easy. Just make sure your equation is balanced to begin with, though. Alright, so some basic rules, pretty simple rules. Don't put any solids or liquids in equilibrium expressions. So if you see solids or liquids, you're just going to ignore them. So let's take a look at this first example. We have H2O liquid produces 2H2 gas and O2. The equation's already balanced. Actually, it's not balanced for us. Let's go ahead and balance it. And by balancing, we'll put a 2 in front of the H2O liquid. So we have K is equal to the product. So one product is H2 raised to whatever power its coefficient is. So that's the second power. And the other compound, is O2. It's just raised to the first power. You don't have to write anything for the first power just because it's by itself. And these are both gases, so I can include them in the equilibrium expression. However, normally we would put the reactant, the H2O liquid, down here. However, the reactant is a liquid, so we actually won't put that down there. We can just put a 1 there, or we can go ahead and write that K is equal to the concentration of H2 to the second power times the concentration of O2. Alright, so this would be our equilibrium expression for that reaction. Let's go to the second example. So here we're going to, again, we want to make sure we don't put any solids or liquids in here. So we start off with K, and let's take a look at our products first. So we have MgCO3, but it's a solid. So in its place, I'm just going to put a 1, just like I did over here for the H2O liquid. Think about why you couldn't put a 0. If you had a 0 in there and you have 0 divided by a number, the whole number is going to be 0, so that doesn't make any sense. So you have to put a 1 there instead. Let's take a look at, it's going to be over the reactants. Let's take a look at the first reactant. That is a gas, and this equation is balanced, so we have CO2. It's raised to the first power or no power, and The second reactant is just a solid, so really that's multiplied by 1. So to simplify this, you can write out K is equal to 1, because that 1 over the CO2, or the concentration of CO2. I got rid of this second 1 right here because that was supposed to represent the MgO solid, but we don't put solids or liquids inside an equilibrium expression, so I could just make it 1, and anything multiplied by 1 is just itself. So this is a simplified equilibrium expression for the second reaction. So let's talk about what that K is. That's something called an equilibrium constant, meaning that if you increase the amount of concentration of the reactants or the products, K can be somewhat adjusted. It's relating the reactants to the products. Here's a big hint. The value of K only changes when the temperature changes. So if I change the concentration, that's not going to change the value of K. It's only when I change the temperature. You'll also see different versions of K, especially when you get into advanced chemistry. KEQ is what the K value is at equilibrium, so it's pretty much what we're doing here. You'll see KSP. That SP stands for solubility product. And solubility product just means that you're forming a solid from, or a precipitate. So here you're forming a precipitate. And a precipitate is anything like we have aqueous solutions and it forms like a solid or a gas or another liquid at the end. The Ka is the equilibrium constant for acids. The Kb is equilibrium constants for bases. Kp is actually standing for pressure. So if you have gases in there, you'll pretty much solve for Kp. And Kw is the autoionization constant for water, which pretty much just means that you have H plus and OH minus. And we've seen this before when we talked about pH for acids and bases. We kind of dealt with the concentration for the product of H plus and OH minus, and that's equal to a constant. It's 1.0 times 10 to the negative 14th molar. And that's just kind of throwback from before. But if you see the Kw, it really represents that 1.0 times 10 to the negative 14th, and it's dealing with water breaking down into H plus and OH minus. So let's do an example in here. Sulfur dioxide gas reacts with oxygen gas to form gaseous sulfur trioxide. Write the equilibrium expression for the reaction. So here we have sulfur dioxide. It's SO2, and we know it's a gas. Reacts with oxygen. Oxygen's a Hunkelbrief, so we'll go ahead and put that O2 in there, and it's a gas, to form a gaseous sulfur trioxide. So SO3, and then that's a gas as well. It says it's an equilibrium, so we'll go ahead and do the double arrows to show that. And it wants us to figure out that expression. But first we have to balance this, so go ahead and take some time to balance it. You'll realize that we actually have 3 oxygens on the right hand side and 4 oxygens on the left hand side. So we'll double that, which ends up having to double this. So we want the figuring out what the expression is. So we have K is equal to the product, which is SO3. It's going to be raised to the second power because that's what the coefficient is for that. And these are all going to be gases, so we don't have to worry about any solids or liquids or substituting 1 for any of these. Put it over the reactants, which is SO2 raised to the second power times O2 just to the first power. So if we want an equilibrium expression, this is what we're looking for. Now let's start putting some numbers in here. So the concentrations are listed below. We want to figure out what that value for K is. So we have to, and this is still going with that last problem. So we know that the K is equal to the concentration of the SO3 raised to the second power over the concentration of SO2 to the second power times the concentration of O2 to the first power. This again was just from the last reaction. So now all we're doing is just plugging in some numbers. So we have SO3, which is given right there. So I'm going to put these in parentheses just so that we know where that exponent is. So it's 3.0 times 10 to the negative third. It's raised to the second power over, let's find what the value for SO2 is. It's right there. 1.0 times 10 to the negative third, and that's raised to the second power. And the oxygen's right here, 2.0 times 10 to the negative third, and that's just raised to the first power, so it's all by itself. So pretty much all you're doing is substituting these concentrations in for your equilibrium expression. So when you put these into your calculator, make sure that you use extra parentheses as needed, especially for this product down here. I'd put all of that into another set of parentheses. If you don't, you run the risk of just getting an incorrect answer from your calculator. So you could have done the work all correctly, however, if it was just a multiple choice or just one of the final answer, the answer would have been wrong. So take your time, put those parentheses in, and when you do this, you should find that it's 4,500. Notice that these were all molarity, excuse me. So part of these just end up getting canceled out. So we have 4,500, and we can put this into scientific notation to keep with 2 sig figs. So it's 4.5 times 10 to the third. That's what the value for K is. And we don't have any units for K either, which is kind of nice. Alright, so magnitude of K, pretty much meaning where it is in relation to like 1. So the products are in the numerator, the reactants are in the denominator. So if K is greater than 1, that means you have a lot of products, the products are favored. If K is less than 1, then you have a lot of reactants, and the reactants are favored. So these are just key ideas to have, especially when you're answering multiple choice. But you can kind of play around with the numbers just to see what ends up happening. So to summarize, K is equal to the products over the reactants, and they're all raised to whatever power the coefficient is. If you have a large K, the products are favored. If you have a small K, the reactants are favored. And that's large and small in relation to the number 1. Alright guys, so have a great day. Take care.